right, here we go. Okay, so we have actually two sets of notes today. I've decided for this first time that we're doing this that I'm going to do two different play pause it videos, and we'll probably do one in the beginning and one at the end is kind of what I'm thinking, but I might change that plan because I'm making this video way in advance. But please remind me on the day of to discuss, or maybe even the next day, to discuss how this went and if you liked having it broken up or if you would have rather had it put into one video. I'd like to get feedback on that for future reference. We're not going to do this incredibly often, but it is necessary sometimes given that I only see you guys 3 times a week. So pause me and write this down. This is it for the first video. All right, so complex numbers. If I ever ask you for it, this is super important. Please write this down, highlight it, put stars, whatever you need to do. If I ever ask you for a complex number, it needs to be a plus bi, not bi plus a. Another thing that people often do is like they'll end up with something like this, and they'll give that as an answer. That is not a complex number. Okay? It needs to be a separate a with a plus in between and a completely separate b attached to an I. So what this would become is that. Okay? This is big, important. Unless you guys ask specific questions on the homework, this might not come up again. Okay? So I'm telling you now, this would be marked wrong. Partial credit. That's full credit. All right? Okay. So the a is called the real part because it is a real number. And guess what the b is called? The imaginary part because it's attached to the imaginary number I. Okay? Another thing to point out that's important when we get down to the fundamental theorem of algebra, every number is a complex number. Every number you have learned so far is a complex number. So 5 is equal to 5 plus 0i, right? So this is a complex number. Every number we've learned so far is a complex number. The real numbers are complex numbers, just the imaginary part, the coefficient b is equal to 0. Okay? So the fundamental theorem of algebra says all polynomial functions of degree n have exactly n complex roots. So this is real and imaginary. Real and imaginary. Okay? I should have done that in pink so it stood out a little bit more. And then we've got the conjugate pairs theorem. If a plus bi is a root, I hope you guys can read that, but that's what that says. If a plus bi is a root, then a minus bi is also a root. Just think about this for a second. When we're solving a quadratic, for example, and you saw in the last video how we took a 4th degree polynomial, we did some synthetic division, we got a 3rd degree polynomial, we did some synthetic division, we got a 2nd degree polynomial. We can use the quadratic formula for any 2nd degree polynomial. Now, why would we if we could factor? But we could, okay? So let's look at the quadratic formula. Okay? When is it that I get complex roots? I get complex roots when b squared minus 4ac is less than 0. So I'm going to write it down here because I didn't give myself enough space off to the side. I'm intentionally leaving this blank, okay? Complex roots when b squared minus 4ac is less than 0, right? Because if this is negative, then I'm going to get an I. But look, I want to find like a bright yellow to highlight this. Plus or minus means I'm going to get the minus b if I have a plus b, okay? So that's why this is always happening. All right, so give me some examples of some conjugate pairs. I'm going to do one and then I'm going to ask you a play pause it question on this. So if I'm given a complex root or 0, actually let's just do all these together because some of these are weird. If I'm given a complex 0 of 5 minus I, then I know 5 plus I is also a complex 0. If I'm given a complex 0 of negative 2i, my a is 0, right? A plus bi. So I'm going to know that 2i is also a 0, right? 0 plus 2i. If you want to write that, I don't really want it to show too much, but 0 plus if you need that there. And then if I have a complex 0 of 6, this one has the b as 0, right? This is where we get stuck. Notice that the b is the thing that changes sign. So it would be 6 minus 0i. So that one actually doesn't change, okay? All right, this is one of my favorite kind of problems to do. You guys are probably going to think I'm crazy. Like I said in the last video, I really like this chapter. This is one of my favorite chapters. I don't love the graphing. Does anybody love graphing? Yes, we're coming up on graphing. But this stuff up to the graphing I really enjoy. And the graphing really shows you the visual of what we've been doing up to this point. All right, so I want to form a polynomial with real coefficients. This is something that people always miss when I give this question on a test. They didn't study this question enough and they don't know how to do it, and then they give me a polynomial that has an I as a coefficient. That's not a real number, okay? So if your answer has an I in it, that means you made a mistake, and I'll show you how that can end up happening. The given degree, so they're telling me that it has to be degree 4 polynomial, and the given zeros, okay? So I need to go back to algebra 1, basically. Where do I want to do this? I don't want to run out of space. I'm going to do it up here. This is a total side note, okay? Side note. This isn't related directly to anything. It's just something that's going to lead us to what we need to do down here. Go back to algebra 1. When we had this, we said x equals 2 and x equals -3, right? Well, down here, they're telling us what x equals. We need to go backwards. Okay, they're giving us the zeros, the solutions, the roots, the x-intercepts. I'm going to try and emphasize that all 4 of those are the same thing as much as possible. We need to go backwards and write the factors, and then we're going to multiply those factors together to write the polynomial. All right, so if x equals 2 is a solution, then x minus 2 is a factor. If x equals -3 is a solution, then x plus 3 is a factor. I would encourage you to rewind that and listen to that again, okay? All right, so here I go. I have 1, so I'm going to write x minus 1. I want to form a polynomial, so f of x equals. I have another 1. I'm going to write it separately because I have to FOIL this out eventually. You could write squared on the first one, but I have to FOIL it out, so sometimes it's easier to see them side by side. Now here's where I need to think about the conjugate pairs theorem. If -4 plus I is a 0, then -4 minus I is also a 0. This also shows me the fundamental theorem of algebra. This is degree, let me use a different color. Sure. This is degree 4, and I have 1, 2, 3, 4 solutions. Degree n solutions. All right, that should match. If you forget about this conjugate pairs theorem, everything's going to get messed up. All right, now here's where it gets slightly tricky. It's not that bad, okay? I had 1 as a solution. I wrote x minus 1. I have this as a solution. I'm going to write x minus that. Right? 1 became x minus 1. So this whole thing is going to become x minus that thing. And then this whole thing is going to become x minus that thing. So here might be a good time to back up and listen to this again. Okay, that's why that was so important. Now I'm going to show you a short way and maybe a long way. I'll probably just start the long way for you. Let me just get started. So we know that multiplication is commutative. Commutative is how it's spelled. There's no N in there. Most people say commutative. It's not an N. So I can multiply in whatever order I want. So I'm going to multiply those two together first because I get a nice little quadratic, right? We also know that addition or adding negatives is associative, right? So first thing, I'm going to just simplify this. X plus, I'm distributing the negative for both of those because I don't like having all those brackets and stuff like that. So plus 4, oops, I almost forgot to write the 4. minus I, and then plus 4 plus I. Okay? So that was the distributive property. Now I'm going to use the associative property. I'm going to associate these together. Okay? Now watch the magic. I'm going to find a different color. I'm going to consider this a first term and these last terms. So I'm actually going to FOIL this. It looks like I couldn't possibly FOIL it, but I am going to FOIL it. Watch what I'm going to do. First times first, right? First times first. Outer, so the plus I and then the x plus 4. Inner, ooh, minus I x plus 4. Look at what just happened there. And then last times last. So this ends up being really nice because these are opposites, they cancel out. And then I can go I'm not gonna, no, I don't need brackets. I'm gonna FOIL this out. And then minus I squared, remember I squared equals -1, right? So minus I squared is gonna be plus 1. Now where the fun begins. This is actually the short way, by the way. I'll show you the long way briefly in a minute. I just have to start distributing everything. I'm going to distribute the x squared. I'm not going to draw arrows for everything. I'm going to combine those as I do this, okay? I'm not going to draw arrows for everything because it's just going to get messy. So I'm going to distribute the x squared. Actually, I will color code them, though. I'm going to distribute the x squared to everything in this parenthesis. So x to the 4th, 8x cubed, 17x squared. And then I'm going to distribute the negative 2x to everything in this parenthesis. So negative 2x cubed minus 16x squared. Remember, this is 17, so minus 34x. And then I'm going to distribute the 1, so that's easy. Distributing the 1 to everything. And then I just have to combine like terms. I like to cross them off as I go, so I make sure I got everything. X to the 4th, I've got 8 minus 2, so 6x cubed. I've got 17 minus 16, that's 1 plus 1, that's 2. Negative 34 plus 8 is negative 26. And then the 17. Okay. Now, let me back up because this FOIL stuff can be confusing. So I'm going to show you a way to do it where you're not foiling this out, but I'm not going to go all the way through the whole process because it's going to end up being the same stuff down here. So if you didn't understand this whole foiling right there, if that seemed to blow your mind a little bit, that's totally fine. Okay, let's back up. What I have to do then is do what I just did in the end. I have to distribute the x to everything, I have to distribute the 4 to everything, and I have to distribute the negative I to everything. So it's tedious, but it's easier. So I'm not going to draw arrows for everything because it's going to be super messy if I do. But I'm distributing the x first. So x times everything, x squared plus 4x plus ix. Distributing the 4, I guess I should continue color coding this. Distributing the 4 to everything, so 4x, 16, and 4i. And then distributing the negative I to everything, so negative ix minus 4i minus I squared. Now, everything that has an I should go away because remember I talked about the real coefficients. If everything that has an I doesn't go away, that's where you know you did something wrong. And you can see you have a positive ix and a negative ix. And then you have a positive I and a positive 4i and a negative 4i. And just like before, that negative I squared is negative 1. So you'll see that this, when I combine like terms, ends up being exactly the same as what we had. Let me see if I can show you it all. Yeah, right here. Okay. It just took a lot more writing to get there. All right, so that's it for this video, and we're gonna see if we like doing it this way with the 2 different videos. Well, I definitely need some feedback on that, okay?